All right. So now let's take a look at how we can simulate this phenomena in OpenFOAM. The version that I'm using is OpenFOAM 2412. The way in which you can access this version is in the link in the description below. You can install the OpenFOAM version. Essentially, once you get to the PowerShell, that is right here. So right now I'm in PowerShell PS. If I just type in WSL, this will come into the Windows subsystem for Linux. And then if I just type OpenFOAM 2412, this will just come into the OpenFOAM environment of version 2412 from openfoam.com. Now to access this particular tutorial, you just need to type in TUT. And if I want to see where these tutorials currently are, I can just type in explorer.exe space full stop, hit enter. What this will do is this will open the file folder where all the tutorial files are present. The one that we are looking for is an incompressible PimpleFoam LES. So you can see this vortexShed right here. Essentially, I've copied that into this particular folder. We've previously sort of discussed what these files effectively mean. What are these properties that we are looking at? I'll just briefly go through a few files that are present right here. The first file that we have, this is blockmesh.m4. Effectively, this file contains the vertices data in an M4 format. This is easier if you want to parameterize the certain vertices. Effectively with blockmesh, you are creating the vertices, then explaining to OpenFOAM how these vertices connect together to create faces, to create the blocks, and so on and so forth. And since this is a two-dimensional case and it is symmetrical in nature, it's easier to do so via a programming interface with variables and whatnot. The next file that we have, this is the control dictionary. So with the controlDict file, you have certain controls which are required for the solver itself, namely what the name of your application is. It's called PimpleFoam. It utilizes your piezo as well as simple algorithms. It starts at 0 seconds, ends at 200 seconds. For every 0.001 delta t, your solution will be solved. And for every 1 second, your solution will be written. The right control here talks about for what amount of steps would you be writing your solution. So for every 100 time steps or for every 100 delta t, you'd be writing the solution here. Similarly, there is something called the purge write. By default, it is kept at 50, meaning that for every 50 times your solution is written, subsequent time step, next one would be retained and the previous 50 would get deleted, is the idea. This is primarily used for saving your storage space and whatnot in instances where it is not required for you to have all the data that is available. Similarly, there is the write format. It's called binary. So all the solution will be written in a binary format in the individual field variable files right there. It's not readable by humans, but it's takes up less storage, so it's easier in that instance. And for the write precision, this talks about after your decimal point, how many number of digits you're going to retain in that sense. Similarly, for time precision as well, after decimal, you're going to retain 6 digits right there. And this control is quite necessary. Runtime modifiable, meaning that as your simulation is running, if you want to change a certain parameter, you can do so. If this is set to false, then the change will not reflect during the simulation. There are a few functions that are present here. I'll talk about these functions in just a bit, essentially explaining what individually these mean in that sense. Let's move on to the next file that we have. This is decompose.dict. This talks about dividing your domain into 4 subdomains or running your simulation in parallel essentially. The method is called simple, where you are just dividing your domain in 2 different subdomains in X direction, 2 different subdomains in the Y direction. Now, of course, since the case itself is 2-dimensional in nature, the third dimension here is kept at 1 right there. The next files that we have, these are fvSchemes and fvSolution. We'll do a deep dive on what each of these are in a subsequent lecture or a subsequent video in that sense. So in the Navier-Stokes equations, we have certain terms in our equations. These are mathematical terms. These talk about your transient nature or rather a convective nature of a certain property. Individually, each of these terms talk about how those constituents of your governing equations are going to be treated. What type of schemes are you going to use, numerical schemes, to resolve for how you solve for these equations in that sense. Similarly, for fvSolution, this talks about the linear solver that you're going to use. Since the field variables here are going to be written in the form of a huge matrix, how are you going to solve for these matrices? How are you going to precondition them or enhance their, make them more diagonal in that sense, so on and so forth. Similarly, the tolerance here talks about the residual control for individual field variable, and ultimately you have your pimple loop that is present here, which subsequently talks about certain numerics, which we will discuss in a further next video perhaps. Ultimately, we have two other files here pertaining to noise point and noise surface. I'll talk about these once we come to the post-processing aspect of it, once we're done with explaining the vortexShed. So now that we have an idea of what the files are that are present here, let's take a look at the shell script that is present right here so that we can run all the commands that are required. Now, shell script here contains data about what type of commands we need to run first of all. So it starts with this particular line here, hashtag and then exclamation mark bin and sh. This is where your shell script commands are going to be sourced from, is the idea. Similarly, this is sourcing where exactly do you need to run all of these commands from this particular directory right here. And this right here is getting the run functions, something like the restore 0 dir, run application, etc. from the OpenFOAM directory itself called run functions right there. One of the first things that this is going to do is it will restore the 0 directory, or it will just copy the 0.org and make it as the 0 folder. In OpenFOAM, anytime you run a simulation, it starts at 0. The reason why we have 0.org is when we want to clean up our file setup using this shell script right there, we don't want the 0 folder to be fully gone. We want the boundary conditions, the inlet conditions to be retained so that we can use the files again and again for the next run. So this is just going to restore that in that sense. Next we have the block mesh. So the block mesh file that we have in here, this is in the M4 format. Essentially idea is this is going to be in the form of variables. You will have all your vertices that you want to write in the form of certain variables which you can calculate for using trigonometric functions. This makes life easier since with block mesh you have to define individual vertices, and for doing so for such a huge and complex sort of a domain that we have, it makes more sense if we can automate this process right there. So that's precisely why we have the M4 format right here, and converting the M4 into the blockmeshdict file is what this command is trying to do. And then this command will just run the block mesh, and this command will essentially divide your domain into 4 different subdomains. And this command right here, get application, is it will essentially fetch the PimpleFOAM application and it will run the simulation in parallel right there, right? Ultimately, we have 2 other commands here which are running for noise, whether it is for a point or for a surface. We'll talk about these when we do the post-processing right now. So to run this simulation, we just have to do /allrun and hit enter, and the commands that we want will be run sequentially right there. So let's come back to this particular simulation right after this is done, and we'll discuss about the results. So the simulation has run. We can see a few things that are generated here. Something about the post-processing. So in the post-processing folder, we can see certain folders are written right there. This talks about the curl point, surface, cutting plane, force coefficients, forces, min, max, and noise. With force coefficients, we have the coefficient data. This is coefficient of lift, drag, due to pressure, due to viscous forces, so on and so forth. We also have the moments for pitch, roll, yaw, and the side force coefficient here as well. Similarly, for other data, we have, let's say, the min max right here. So min-max is just giving you the maximum value for magnitude of view and the pressure. It is also giving the location, which processor, maximum location for maximum, and the processor where it is situated, so on and so forth. So you can get this amount of data from your particular simulation in that sense. And then ultimately for the noise, we have also written a lot of data for these observers as well as on top of the surface. And similarly, once this data is fetched, we will see this talks about the curl of your pressure, then root mean square of your pressure, and so on and so forth subsequently. So let's take a look at what our simulation essentially looks like in ParaView. Cool. So what I have here with me is a representation of what this simulation looks like in ParaView. So the way in which I have defined or showcased this particular contour that I have right here, this contains data from Streamlines as well as Glyph. And I've just opened another instance of OpenFOAM with ParaView to just show the cylinder so that you can see what's happening as the pressure data on top of it. So one of the first things that you would do is create a .foam file. So to do so, we can just go to the terminal. So touch and then cylinder.foam, and this will just create the .foam file that we are using here. And you can import that .foam file into ParaView or use your Windows to configure and open it with the paraview.exe file present in your programs and features. Once you have it opened, it's necessary that you choose the decomposed case. Since this is run in parallel, you would require it to be a decomposed case. Another thing that I've done here is add the streamlines on top of it. It is this particular option. And with streamlines, the velocity vectors for a particular point cloud. So if I show the sphere, this is encapsulating the entire domain that we have right here. And this point cloud is of radius 0.5, somewhere around the center of this particular domain, so on and so forth. Similarly, I have also added something called Glyph, which is this right here. So with Glyph, what we've done is an orientation array of velocity with scaling array of pressure. Notice that the pressure has a negative value as well as the positive value, maximum being 0.001, minimum being negative 0.001. So your velocity vector or these glyphs will effectively be scaled accordingly with that. So once these are getting scaled according to those, you essentially want the scale factor to be a little higher. So for example, if I want to do no scale array and just hit apply, perhaps not as big. Yeah. So you'll see that the streamlines that we have right here are looking much more oriented in the direction of velocity itself. And we'll see that there are these recirculations that are also getting created right there, right? Of course, this is a 2D case. So we just have these glyphs present on the plane where cylinder starts and plane where cylinder ends itself. But along with that, we also have, the velocity profile that is getting created closer to our surface as well. This is a good representation of what your velocity increment is looking like closer to the surface, so on and so forth. So very close to the surface, we'll see what the thing looks like. Another thing that I can do here is perhaps have a scale array of velocity itself. Just a bit, there we go. So what this is trying to do here is it is scaling according to the velocity that we have. Perhaps we will have it at 0.05 right here. So this looks a little higher, maybe let's do 0.025. Notice how I'm trying to do it in the increments of 2 here. So closer to a surface, the velocity is as low as it gets. If I increase the stride to every 1 point here, so this will make a glyph for every single point of mesh that you have inside your domain. To avoid that, I've just reduced that to 5. So what you can see closer to your cylinder right here is representation of this boundary layer itself, and very closer and closer to this right here, we'll see certain recirculations as well, right? So this is one way in which we represent how our flow is effectively looking like in that sense. The way in which I've displayed this pressure, for instance, if I just want to go to the cylinder.foam right here, I want to scroll down. So there is this option, the color legend properties. So in here, I've just added the pressure, the units as Pascal. I've given the font as times, and the color bar thickness and the color bar length I've changed a little bit. So if I do 0.3, you will see that this is right here. Similarly, I've also done, one final thing, a data range label of minimum and maximum at the float sort of format here. So this is how you can accomplish this as well. So this is what the flow physics essentially looks like around your particular simulation right here. If you want to add at what time you are currently at, so what you can do is control space and annotate time filter. You can just hit apply, and this will give you at what time step you're currently in on the top left of your simulation right here. Also with the stream tracer, perhaps if we want more, or maybe this is good enough. We have 10,000 of these streamlines that are present right there. This is good enough. So what we will do right now is we will create an animation of what this vortex shedding looks like right behind this particular cylinder right here. So what I will do, I'll go to file, I'll say save animation, and we'll call it, let's say, shedding.mp4. So frame rate here is quite necessary. For our instance, we only have 50 data points or 50 different time points right here. If I want to do 8 frames per second, I will have a video somewhere around 6 seconds, close to 6 seconds. Or if I just want 16 frames per second, that will be fine too. Let's stick with the 8 frames per second and hit OK. So what this will do is it will write the animation at its pace. It will change the time step accordingly. Resolution will automatically be changed with respect to how your screen size is essentially. So once this animation is done, let's take a look at that. All right, so this is what the vortex shedding essentially looks like.